Hi everyone, welcome to class number 40 of Physics 218. So today we're going to wrap up our brief introduction to nuclear physics. So last time we talked about some nuclear terminology and interactions. We also talked about calculations of nuclear binding energy. I want to follow that up today by talking about the curve of binding energy, and then that'll lead us into a discussion of nuclear processes. So these include nuclear decay processes, as well as fusion and fission. And then we'll talk along the way about some applications of these ideas, which I hope you'll have the opportunity to pursue in more detail in the future. So recall that the binding energy B is the energy you need to add to a given nucleus to separate it into its individual component nucleons infinitely far apart. This arises, right, because the sum of the masses of the individual parts is larger than the mass of the nucleus as a whole. It turns out that for investigating questions of nuclear stability, it is useful to plot the binding energy per nucleon versus the total mass number A, and this is a thing that's called the curve of binding energy. And the reason we want to look at this, right, is that otherwise, if you think about the interactions involved, right, the more nuclei I have, the more nucleons I have in a given nucleus, the more interactions I might have. And so you would expect roughly that the binding energy would go up as you have more and more nucleons interacting. So that's why we plot B divided by the mass number, and we'll go now to my laptop where I'll show you this curve for known naturally occurring isotopes. So this is that curve of binding energy where we're plotting the binding energy per nucleon versus the mass number A. There's a few things to notice. So notice that there's a maximum here at about 8.8 mega electron volt per nucleon for iron. Right? Notice that the curve of binding energy, sort of aside from some funkiness at very small mass number, generally increases up to this maximum and then thereafter decreases. You might also notice that sort of after a certain point, after about 8-ish MeV, right, the curve of binding energy kind of just levels out and sort of does the slow decrease thing. So where that you can think of that as evidence for the short range of the strong interaction, whereby if I add more nucleons, it's not as though each nucleon that I add actually interacts with all of the other ones after a certain point. There's a few other things that I wanted to mention, and it's sort of this curve gives some evidence for how one can get more stable nuclei. So for small nuclei in general, like down on this end, right, in general you can get more stable and increase your binding energy per nucleon by getting heavier. That's what nuclear fusion is all about, as we'll see. It turns out that in stars, right, you can get fusion to get all of the elements up to iron, this maximum. Conversely, if you're a heavy nucleus, you can get more stable or increase your binding energy per nucleon by getting smaller. And as we'll talk about in a sec, there are processes like alpha and beta decay that can do this, as well as nuclear fission. I'd now like to briefly discuss some important nuclear processes. The first one I want to look at is called alpha decay. Now, an alpha particle is none other than a helium-4 nucleus. So let's note that. So an alpha particle is a helium nucleus. And the general schematic of alpha decay looks something like this. So we start with some initial nucleus, so some parent that, so I'm using X as a generic atomic symbol for sort of the nucleus that's going to undergo this decay. And then that, right, undergoes decay and changes to the following. So Y is what we call the daughter nucleus, and then the atomic number decreases by 2, the mass number decreases by 4, because we have our alpha particle ejected, and usually there's some energy that's released in this process. So this is a label for terminology. This is what we call the parent. This is the daughter. Yes, that's gendered. I'm not sure why where this terminology came from, but we're kind of stuck with it. Here's our alpha particle. Okay. So a few things about this, right? So it's generally sort of tricky to predict, that a given nuclear process definitely will happen, but it is quite possible to say that a process can't happen based on fundamental physical principles. So namely, if we consider, right, the parent nucleus as sort of the initial system and it's isolated, right? If it's an isolated system, right, you cannot have a situation where the products have more energy than the parent. So conservation of energy puts limits on what's possible. And so, right, since we can think about the rest energy, we can relate the rest energy of our particles to their mass, we can write a conservation of energy criterion in terms of the masses of our constituents. So, namely, we need to have the atomic mass of whatever our parent was. That's got to be greater than or equal to the mass of the atomic mass of our daughter plus the atomic mass of our helium. To get alpha decay. Okay. And when I'm writing the masses here, these are the atomic masses, where as we mentioned in the example last time, the atomic masses do include electrons, but there are sort of no changes in electrons going over this process, so we don't need to worry about keeping track of them, and we can just look at the atomic masses. Now, there's a particularly good real-world example of alpha decay. Namely, most smoke detectors contain a radioactive isotope, americium, that undergoes a decay. And let me write down the alpha decay that americium undergoes, and then I'll cut to my computer where I can show you a schematic diagram for a typical smoke detector. And so it looks something like this. So americium, so 241, undergoes an alpha decay to neptunium, which is NP, and that's 23793 plus our helium nucleus. And it turns out there's also a photon that's released, so a gamma photon that's released in this particular decay. So let's go to my computer now, and I'll show you how this process gets used in smoke detectors. This is a schematic diagram for a typical ionization smoke detector. This is the most common kind you can find in, say, hardware stores. So this kind of smoke detector has an ionization chamber that is exposed to the ambient air. And you have also this americium source that undergoes alpha decay via the mechanism I just described. Now, when you have these alpha particles flowing into the chamber, those alpha particles tend to ionize the air molecules inside. What you then have is these metal plates that are connected to a battery that applies a potential difference across the plates. As you know, charged particles, so those ionized air molecules, move under a potential difference, so that creates an electric current that can be measured. When you now have smoke that comes in here, the smoke particles tend to bind to some of those ions, and they don't move as easily from one plate to the other. That ends up decreasing the current, and that's something that you can measure, and that's what trips the alarm. Now, just if I can be permitted a moment to editorialize, now that you know how these things work, especially if you live in off-campus housing, you should always make sure that you have working smoke detectors and test them on a regular basis. And I say that in part because when I was in college, I had a high school classmate who was attending college somewhere else, and sadly he died in a fire. And it turned out that where he was living, he did not have a working smoke detector. Perhaps that would have saved his life.